Like,
Okay.
जब से start कर दी वो
Huh.
चीजें आ जाए.
Okay. So, welcome everyone. So, uh, whoever has joined and whoever is watching now. So, uh, this is the live session of the course High Power Multi-Level Converters, and so you can ask questions and clear your doubts. We are already engaging ourselves in answering your questions in the discussion forum. But since this is a live session, so it is encouraged, and I would request you to post your doubts and whatever questions you have in your mind. Just write it in that chat window, and we will answer those questions. So before we proceed, we have already got some questions, and these questions I will now go through. And so there are like 3-4 questions. So the first question is from an email, Nish Sharma. So he is asking, in an MMC with 6 cells per arm, that is 3 in upper arm and 3 in lower arm, employing phase shifted PWM, is the phase shift between two carrier signals in upper arm equal to 60 degrees? Okay, and this is correct. Whatever he has written is correct, because in phase shift PWM, the angle between two carriers is 180 by n. So there are 3 in upper arm, and so the uh, upper arm is a separate controllable voltage source, and the lower arm is a separate controllable voltage source. So the upper arm can be treated as a separate phase shifted PWM switched converter. The lower arm also can be treated like that. So that's why they are completely independent of each other. So this is correct. Okay. So the next is another question is from Ravi. So he has asked, in the 6th week teaching slides, slide number 25, you have shown reference waveform for upper and lower arm of an MMC. Can you please explain how the references are derived for DC to AC MMC operation? Okay, so if you go to, so I think this is the slide he is asking. So uh, so I so let me, okay, no, sorry. So this is where you can see what we have already covered. Okay, this is Subhashish. He is a PhD research scholar with us. So anyway, so you can see here the reference. So this waveform here is applicable both for AC to DC as well as DC to AC operation. Okay, this waveform here, right? Uh, so if you see here, how do we understand this? Basically, the idea is that you have this. Suppose it is working for a. What he has asked is how do you how the reference is derived for DC to AC MMC operation. So okay, so he is asking how do we get the reference waveforms? Okay, the reference waveforms is obtained from the controller. Okay, we have not talked about controllers in this course because I wanted to keep the whole thing separate. Okay, I wanted to focus more on the converter topologies and PWMs, but not going into details of the control system, because the control system for the multi-level converters is the same as a conventional VSI or VSC. Okay, there is no difference. The only difference is the switching action that takes place. So when it comes to the switching action, then the control system is slightly modified at the end. So this waveform, this reference waveform, so if you ask me how did I obtain this waveform, I will say that suppose if it is a motor drive, the motor drive, if it is a vector control motor drive, then you have a omega star, and from that omega star, then you go through a series of control blocks, that's the speed reference, and then you ultimately get a VA star, VB star, VC star. That is the A phase reference, B phase reference, and C phase reference. This is where you get three sinusoidal waveforms, right? From that VA star, VB star, VC star, suppose you want to implement space vector PWM, then you have that max min algorithm and you generate a new VA ref, VB ref, VC ref. Okay. Again, similarly, if you want to, from that VA ref, VB ref, VC ref, if you want to run a multi-level converter, then what you do is, so that VA ref, VB ref, VC ref is this sinusoidal waveform which is shown in the in this slide here. Okay, this is the VA ref, VB ref, and VC ref. I mean, it's only the VA ref that I have shown. VB ref and VC ref are not shown in this. So for a DC to AC converter, suppose this MMC is driving a motor, that VA star, VB star, VC star, or VA ref, VB ref, VC ref is what comes to the switching logic block. Okay, the switching logic block then takes this VA ref, VB ref, VC ref, and then it will do this phase shift PWM or level shift PWM, or if it wants to do something else on that, so it creates a switching logic, and based on the switching logic, then it will send it either to the DSP or through an additional FPGA or something like that, and then the gate pulses will be sent to the individual cells. Okay, so therefore this is how it works. It is a very standard vector control or whatever control strategy you wish to run it. So there is no difference in the control system. Okay, the controller does not see any difference. Only the switching logic changes when you go with this kind of a approach. Okay, so there is also one question. Yeah, what? Okay, let me go to the question, but before that I want to finish off this email. So there is someone, Ravi Kallu, so he is saying that we take third year student, which topics should I take to publish papers for MMC, CHB, NPC of IEEE standards. I want paper of such type so that extension from this experience and knowledge I can successfully apply to some fellowship. What are the industrial proposal examples you would suggest me to apply for something application in India? Where can I get such information online, or should I join? You see, the first thing I will suggest you that when you are, so since you are in a BTech EE third year, it's very good that you are thinking of publishing papers, but the first level I will say that you try to understand and try to get knowledge. Publishing paper is a secondary or something which it comes next. Okay, it is most important that first you learn, build up your knowledge, have confidence on whatever you are studying, then you go for publishing papers. Okay, now so at your level of you said that you are BTech and third year student, so I think at this point of time for the next 1 or 2 years, take some like you have taken this course, so improve your basics, And for example, in the fourth year, I can also say that in your fourth year, you can take up a project which is related to some of these multi-level converters so that you can get more insight. Okay. Now, so you can take up some industrial problems. So there are many industrial problems. So if you see the application of voltage source converters for industry applications. So voltage source converters are used everywhere. So it is used in, say, integrating PV and wind energy sources. It is also used in motor drives, traction drives, for example, and many other applications. So take up an example and go through the literature, identify a problem, and then try to attack that problem by applying the knowledge that you have gained, for example, through this course or some other courses which you have studied in your course. So I will say that this is how you get more experience and more understanding of the operation of the, um, um, also, I will say, if you want to join any company, of course you should join a company. Definitely, because as an engineer, I think your knowledge is not complete unless you work in a company with a real life problem. Okay, there you will see many of these design constraints. You will face it yourself, many of the design constraints that a designer faces, and only then your knowledge building is complete. Okay, so we in our course curriculum in, for example, IIT Delhi, we do a lot of laboratory sessions, and all our students, all the research students, they develop their own laboratory hardware. Okay, because we would like to give them this flavor. Only then they understand that, okay, fine, this is the constraint which we have to live with. This is the real world. It's not like doing some simulation and theory. This is the real world. So as engineers, we have to build things and we have to make things. So these are the constraints under which we operate. So many times this uh, practical practical constraints and practical design ideas are very helpful. So then they realize that, okay, whatever I, but at the same time you will see that the practical follows very close to the theory. So unless you know the theory very well, you will not be able to do the practical exercise or building a converter. But of course, many times when you build a converter, you have to apply your mind. I mean, very simple mind, like how will I, uh, how will be the enclosure look like? How should it be? How will I package the whole thing? These are very practical questions. So where should, so if you are building a converter, in which, on which side should be the input, which side should be the output, how it can be user friendly, because when you build once, it should be also easily, kind of like, if you want to service it, it should be easily serviceable, it should be easily integratable, like that. So those things also are very important. So, but you will get a lot of understanding about this when you go to a core company where you are involved in the design, fabrication of such converters. So I would suggest that going to the industry is definitely a very good option, but you can also go for some fellowships for your higher studies. That is also a good idea. Now, there is one more question. In capacitor voltage balancing using LSPWM, after sorting the cell voltages, do we have to keep jumbling the carrier signals applied to the cells according to the sorting algorithm results? No, you don't have to jumble. You don't have to jumble the carrier. There is only one carrier. What you are jumbling is based on the sorting algorithm results that you get. Basically, you are getting a series of pulse patterns. Now, because the level shift PWM, it will give you, suppose you have cell 1, 2, 3, 4, it, and your sine wave is going like this. So then you know that, okay, these are the pulse patterns for each cell. Now what the sorting algorithm does is that it will distribute this pattern to different cells based on the current state of the voltage on that cell. So you have one cell, so you have a pattern for one cell, you have a pattern for another cell. So you will just distribute. Okay, so which cell will get what pattern will depend on the instantaneous voltages on that and the direction of the current. Okay, so that is what we have explained in the PPT in the lecture. So the carriers don't change. There is in fact a single carrier. Okay, in level shift PWM we have said that in level shift PWM we can bring all the modulating waveforms inside one carrier. That's what we do. We bring everything inside one carrier. So there is a single carrier. There are no multiple carriers are even needed. But this pattern of for the cells, the PWM pattern for the cells, that we shuffle. That is what we shuffle, go on shuffling. So we see, okay, this capacitor is less charged, so let's put this pattern to this capacitor. The other capacitor is discharging, so let's put this pattern here. So this is what we do here. Okay, fine. Now there are some questions which are coming in the chat window. Okay, first, what is the question? So, SVPWM has an equal share of zero voltage vector, but third harmonic does not have. Why is it so? Okay, so why is it so? Fine. So if you see here, SVPWM, of course, so what you have done with SVPWM is that in the modulating waveform, you have deliberately, by putting this max and min algorithm in the modulating waveform, you have deliberately made sure that your upper and the lower distance from the carrier, that those two distances are equal. You have made it deliberate. That is what you have done in space vector because those two are controlling the zero vectors. If you see the carrier like going like this, and then you have the modulating waveforms. Now the distance of the maximum modulating waveform and the distance of the minimum modulating waveform from the upper and lower boundaries of the carrier, these two distances in space vector PWM are always equal. You have made it deliberately. So therefore you have made sure that it has an equal zero vector durations, upper one and lower one. However, so that part is taken care in space vector PWM. But in case of third harmonic addition, there is nothing like this. So you have just simply added the third harmonic. So you have not made sure that the upper and lower parts are equal. So that is the difference. Okay. Now, why SVPWM has a better harmonic profile? Yeah, so then you have to do this. I will suggest you see the book by PWM book by I think Holtz and Lippo. That book, DG Holmes and Lippo. There is one big book on pulse width modulation. Also, it's a big book. So that book, if you go through that book, you can do this analysis. I have not done in the course, but you can do the analysis, and there by using the Bessel function approximations you will be able to understand that okay, that by putting these zero vectors equally you get the best harmonic performance. Okay, the magnitude of the fundamental does not change, but the best harmonic performance you will get when you put the two zero vectors equal. Only this will be visible only at the switching frequency band. Okay, not at the fundamental does not change, fundamental remains the same, but at the switching frequency harmonics band you will see there is a change of pattern of the harmonics, little bit change of pattern when you make zero vectors equal or when you make the zero vectors unequal. Okay, so this why we have not covered, because see we are not very we are not very much into that analysis, like what is the exact harmonic pattern of the or what is the exact magnitude of the switching frequency harmonics. We have never talked about it. This is simply because of the reason, if we put filters, we eliminate all the harmonics. Okay, so we are not concerned about the exact magnitude of the harmonics. We are only concerned about the position of the harmonics. In particular, with multi-level converters, we are just thinking like where is the position of the first band of harmonics. So exactly how the harmonics are, this will not be useful for this course. However, if you have a very low switching frequency application, if your switching frequency is very low, it is very close to fundamental, then you have to be very careful, like what is the exact zero duration. And so then this factor is important, then this factor becomes important, and there we have to talk about symmetries in the waveform. Okay, so you should have symmetry in the wave. So you should have, for example, half wave symmetry, you should have odd symmetry. So whatever happens at theta should happen as f of theta plus pi. So there the exact position of the pulses, the what I should say, the position of the pulses, the duration of the pulses, with all these half wave symmetries, those become very important. We have not covered it in this course because in multi-level converters, the effective switching frequency is so high that we are not bothered about it. But if you work with a conventional voltage source converter at very low switching frequency, for example, if your fundamental frequency is 50 Hertz and you are working at 300 Hertz, 350 Hertz as your switching frequency, then you have to be very precise, like where is the harmonic, or what is the symmetry, how we maintain all the symmetries. And sometimes people go with a selective harmonic elimination, so they put a notch in the waveform and they put alpha 1, whatever, wherever you put the notch at alpha, you put exactly the same notch at 180 plus alpha, and like that. So put a notch, so start with a square wave, put a notch and put another notch in this one, and then you see that okay, what are the three phase symmetries happening. So whatever you do at alpha, you should do exactly the same thing at 120 plus alpha for the B phase, and the same thing for 240 plus alpha for the C phase. So these waveform symmetries also play a very important role to maintain all the symmetries. So that we have not covered because within the scope of this course, it is not possible to cover it like that. So, but if I get a chance, I will cover it in some future course where how you control a converter with very low switching frequency application. That is possible. I mean, you can see some of the books and references. Okay, now good morning, sir. I have a doubt in calculating the levels of MMC. Okay, what is the doubt? Oh, how you have a doubt in calculating the levels of MMC. So see, it's very easy. Like suppose you have an MMC with half bridge cells. Now, you from a half bridge, from a single half bridge, you can get two levels. You can get 0 or VD. So you have one half bridge. Now you connect another half bridge, second half bridge. So from the second half bridge, you can get again 0 and V from the. Now you make an addition of these two. So you can get 0, VD and 2 VD, right? So from two such half bridges, you get three levels of voltage. Now you can connect another half bridge. So if you connect another half bridge, that third half bridge also will produce independently 0 and VD. So now you will get 0, VD, 2 VD and 3 VD, right? So therefore, for a half bridge MMC, if you have n number of cells, you will get n plus 1 number of levels in the output voltage. Okay, so this is how we calculate it. Okay, the third question, please explain a closed loop operation of MMC for an example full bridge topology based MMC for AC to DC conversion. So when AC to DC conversion is happening, so you don't have to go to a closed loop operation of MMC to understand it. You just see the closed loop operation of a voltage source converter, okay, which is sometimes called the front end converter. Okay, the front end converter, what it does, the front end converter is connected to the grid and it maintains a DC link voltage, okay, VDC. So the VDC star, the DC link voltage uh, is the reference. So how much DC link voltage we should try to maintain, and in order to maintain, so VDC star is the reference to this control system, and the that in order to realize that VDC start, we will take some active power from the grid, okay, from the front end converter. So this is an AC to DC conversion. So we will take an active power and we will take the active power at unity power factor. So the VDC start, if there is a load connected to the DC bus, then that DC bus will fall if we are not giving enough active power to the DC bus, and the DC bus will rise if we are giving more amount of active power than what it's required. So therefore VDC start is our reference voltage for this whole control system, which ultimately through a series of conversions and alpha, beta to DQ and conversion, ultimately we will get a VA star, VB star and VC star, which we will feed to the PWM logic to fire or to control the 6 IGBT switches. That's it. In case, so this is for a conventional voltage source converter, like acting as a front end rectifier. The same control logic, you will just take it and then we will put it into the MMC with an additional modification. What is the modification? That VA star, VB star, VC star, that now has to be catered, or that has to be modified for so many cells. So then we use either level shift PWM or phase shift PWM, and then we have additional sorting algorithm. If suppose MMC is there, additional sorting algorithm we will put, and then we will control it. So the core of the control system is not changed. Only the switching logic changes for MMC operation. Okay. Okay. No. For the sorting algorithm, we need to know the direction of the arm current in MMC. Correct? That is right. For half bridge topology based MMC, where should I put my current sensor? So you should put your current sensor at the ends of the arm. Okay. So either you put at the beginning of the arm or at the end of the arm where you are connecting the inductor, arm inductor, or you just sense the arm inductor current. That's it. So then you will know what is the direction of the current, okay, through the arm. Okay. Hall effect based current sensor has a voltage stress in switch. Not really, not much. Hall effect based current sensor. So you can use a Hall effect based current sensor. It's not much. So we have used Hall effect current sensor and it works quite fine. Okay. So if we use full bridge cells in arms of MMC, then the carriers and phase shift required in phase shift and levels. What is the question? If we use full bridge cells in arms of MMC, carriers and phase shift required in, yes. Yeah, so you can see the formula of it because full bridge cell in arm of, so it does not change. You see, this is where some students are making a mistake. Like the full bridge and half bridge, it does not change anything regarding the PWM strategy. Okay, because the full bridge, when you use the full bridge or a half bridge, basically each cell is a controllable voltage source. Okay, whether it is a full bridge or whether it is a half bridge. So each cell remains a controllable voltage source as it is. So that controllable voltage source occupies a portion of the level shift PWM, the portion of this thing. Now, if I will modify this statement. So if it is a half bridge, it is comparatively easier because you don't have to control two switches only. In full bridge, so then I will ask you to refer to those slides where the cascaded edge bridge, we have controlled the cascaded edge bridge, all the four switches in the cell. So there was one slide where I have, when we were talking, when we are talking EHB, you will see that there is one slide where all the four switches, how we control for a given modulating waveform, all the four switches, how we control is explained. Please go through that slide. If you go through that slide, then you will understand that, okay, given a modulating waveform, how do we control all the four switches in a full bridge, In a half bridge, it is relatively simpler because then you have to control only one switch, the other switch is complementary. Okay. Um, yeah, so just go through it. In case you find you cannot do this, you ask me in the forum. Okay, then I will again, because I do not have that slide right away in front of me, so I otherwise I would have explained to you how the four switches, but it is, I have explained it in the when I was talking about the cascaded edge bridge, this one, go through that slide. Okay. That's the elimination. Since half-bridge cells have DC content in voltage, does the elimination of this DC content in full bridge benefits in the operation, and how to utilize this DC content in full bridge? The DC content in half bridge and full bridge. Okay. Now you see here the DC content in the half bridge operation. So the DC content in the half bridge does not come in the line voltage, so or the output of the voltage. So the DC content in the half bridge, remember full bridge can also have a DC content. It is not that the full bridge cannot have a DC content. Full bridge, if you shift the modulating waveform a little bit, full bridge can also produce a DC offset. Okay, so half bridge by default there is a DC content. Okay, now this DC content in the half bridge is something which is detrimental in terms of during the fault condition. In full bridge, this DC content may be present, it may not be present. Now we can utilize this DC component of the full bridge during fault condition, where we deliberately, if there is a DC shift of the voltages, we can deliberately use a full bridge to nullify the effect of the fault condition. Or so there has been some recent research on HVDC fault with MMC half bridge cells. There they have found there is a potential, there is a shift of potential. Okay, when there is a half bridge, so when there is a fault on the DC pole to pole fault and the half bridges are working, so there is a shift of potential, and full bridges can work very well there, because full bridges can provide something like sort of a counter DC, because full bridge can produce a DC as well as an AC, whereas half bridge can only produce a unidirectional DC. No, so the full bridge will produce a DC in the reverse polarity in such a way so as to uh, minimize the fault current. So in that more functionality as compared to a half bridge. Okay, that's why newer generation MMC based HVDCs are coming with full bridge. However, full bridge has a big disadvantage, and that disadvantage is what you do with a half bridge. With full bridge, suppose when you are bypassing the cell in a half bridge, only one switch you will use. Okay, so there are just one switch you turn or bypass the half bridge. But in full bridge, if you have to bypass the cell, you have to use two switches. So losses in the efficiency based converter is more. Losses is more, efficiency is less in full bridge as compared to half bridge. So that's why half bridge has a better efficiency, but again at the fault condition, full bridge offers you more functionalities. So in that way, benefits the operation of the converter. Okay, then there is what is this next question? Is it possible to implement any type of multi-level converter in electric vehicle charging station? What is the cost to implement? We don't know. What is the cost? We don't know, because it is very difficult to estimate cost. Cost depends. So that is why I think we should be a little bit uh, uh, you should go to the industry. My suggestion to you is that go to the industry and work there for some time. Then you will understand how costs are calculated. So people from a technical background, purely from technical background, they estimate some cost. But there are many other costs which, unless you go to the industry, you will not be able to say what is the cost. For example, I, from my experience, I can say a substantial cost is uh, is incurred during testing of the converter. So you will go on repeating many types of tests. Some tests it will fail, the converter will fail. Some tests it will not perform as per the standards and something like that. So then it will come back to the designer once more. Okay, it will come back to the designer and they will say, no, this is failing. This is not as per. So your temperature should be up to 50 degrees centigrade. It is going up to 70 degrees centigrade. So something like that. And then they will say, it will come back to you as a designer, and you have to make modification to the design. And again, it will go through an iteration. So it goes like this. It will go like this for several iterations, and then only the final product is obtained. So therefore, estimating the cost from the bill of materials of or the cost of components is not the correct justification. Okay. Uh, so just by saying that, okay, the cost of the material, this capacitor costs this much, this IGBT costs this much. So if you add all these components and you make the cost, okay, let us put some profit margin and then it goes, this is the total cost of the converter. We cannot say. Definitely we cannot say, because there's a lot of iteration that goes through in making a good quality converter. So when you say a good quality converter, it must meet all the standards. It must go through rigorous testing, so there will be several versions of the converter, first version, second version, third version. And so finalizing the cost, and ultimately after all these things, this is only the kind of like making cost and all. And after all this, there will be some business people who will understand the market, and based on the market they will launch the product based on some cost, which probably you will have little influence on. So telling the cost of a converter is very difficult. I will say it is next to impossible. You can estimate from but I can say multi-level cost converters for this, say for example this MMC for an HVDC application, these can cost several crores, maybe hundreds of crores. Okay, we don't know. I cannot comment on that. Okay.
Yes, it is possible to implement any multi-level converter for EV charging.
Yes, definitely it is possible. Now, when you say EV charging, then you have to see what voltage level. Now, see, nowadays we are doing EV charging at 230 single phase voltage level or 400 volt three phase. But this is going to change. Okay, as the people are saying that, okay, we want to charge EVs faster and faster. We want to charge the whole battery in 10 minutes or 5 minutes, like what we do in the petrol station. Then what will happen? You have to go for a higher voltage. You have to go with the higher voltage, because 230 volt household socket has a certain limit. A 400 volt system has a certain limit, maximum current that you can draw, or maximum power that you can draw. So when you go with a higher voltage, so then you will say that, okay, let us integrate directly to the medium voltage level. Say you integrate it at 11 kV, or you do it at some other voltage levels, so medium voltage level. Then the multi-level converters start to appear like promising. Okay, at 230 volt, probably multi-level converters is not so promising, because we have devices which are already MOSFETs or IGBTs are easily available at 600 volt, and also IGBTs at 1200 volts. These are easily available. So then when you say the multi-level converters, people will ask you, why will you go for so many switches at such a low power, low voltage rating? Because we have a very established voltage source converters there. Why will you go for a multi-level converter? When you go with direct integration to the medium voltage level, then okay, fine. Then now we have to see what are the availability, what are the possibilities of switches, what are their voltage rating, what are their current ratings, and how quickly we want to charge electric vehicles. or do we want to charge only a single vehicle, or do we want to control multiple vehicles at the same time? So then the possibilities open up for the multi-level converters, and then you have to see what type of devices will you use, 1200 volt, 1700 volt, or 600 volt. Okay, how many devices will you use, what are their voltage rating, what are their current ratings, something like that. Then you can decide, fine, okay, this is a possible topology. We have to see what is the efficiency, what is the fault tolerant feature. Okay, that is also important. Like, suppose you are putting one converter and one switch breaks, and then you say that okay, the converter is unusable, that people will not accept. Okay, so they want that, okay, if you are putting a multi-level converter and if you have switches which is kind of like destroying, you should have something inside the converter which will run the converter maybe at a reduced power. Okay, so that is also something which you should, but definitely for future electric vehicle, power converters, multi-level converter is a very promising solution at medium voltage level. Okay. Okay. Can I say for third harmonic injected sine PWM, we need not to control the amplitude of third harmonic in closed loop operation. We need not to control the amplitude. I will say, I will modify your sentence, and I will say that you make your third harmonic magnitude 1/6 of the fundamental harmonic magnitude. This much I can say. We are not controlling, we are just blindly adding. Suppose you have a modulation index of m for the fundamental, you just add m by 6, okay, as the third harmonic, and then you add. And this third harmonic, what you are adding is the only purpose of it adding is to maximize the DC bus utilization. Okay, so this is the only purpose. There is no other purpose. Okay. You are not improving the PWM or harmonic spectrum and something like that. You are just improving the DC bus utilization, which you get 15% more if you add the third harmonic. Okay, so when you say that control the amplitude of the third harmonic, you are not controlling the amplitude, you are just adding the 1/6. Okay. Okay, please explain once more in MMC what happens when DC side is short circuited or has a very small value. How back EMF come into existence to limit the current. Okay, so so you have arms, right? So MMC, if you see, let me see if I can draw it. So you have this. I'm not drawing the arm inductor. Do the arm inductor. And then you have this. And there is a DC short circuit. Okay, now I am not drawing the C phase. So this is A phase, B phase, and then there is a C phase. Okay, so suppose you have a short circuit, right? So what happens then is that, how do you change the color? So then, okay, no, sorry. Okay, let me do it. So suppose you have a short circuit condition. So what happens is the current will flow like this here, and it will go back like this, right? This is one possible uh, direction of flow of the current. Now, if you have a half bridge, right? If you have a half bridge, then once you detect that there is a fault, then you will shut off the IGBTs, right? Once you shut off the IGBTs, then what remains in the half bridge? So you have this and you have this, and you have shut off the IGBT. So you have cut out this one and you have cut out this one. So what remains is nothing but these diodes. The diodes are still uncontrolled devices and they are in the circuit. So therefore the diodes will conduct. Okay, as you can see here, the diodes will conduct. So this controllable voltage source in presence of the fault, this will the problem there is this will act as a diode, uncontrolled diode rectifier, and so basically there is no control over the voltage that you produce from the cells. Now when you go to the full bridge operation, of course you can do the same thing here. You can shut off the IGBTs and then it also becomes like an uncontrolled device. But in a full bridge, what we do is one possibility is that we don't shut off the IGBT. We allow the IGBTs to remain as it is. And then what we do is that now the full bridge, so suppose if you see, the full bridge has bidirectional voltage capacity. So it can generate a positive voltage, it can zero, or it can generate a negative voltage. But the half bridge can generate only zero and positive voltage. So the half bridge was basically during the normal operation, this was the voltage which was given, and the half bridge was kind of these arrows. It was generating the arrows. Now, when there is a fault with a full bridge operation, the arrows can be immediately reversed. Okay, so the voltage generated by the full bridge is kind of like a back EMF. You can make it operate like a back EMF, which is basically opposing this line voltage. The line voltage is the one which is driving the fault current. Okay, as I had just drawn, the full bridge voltage, it has the capacitor inside it. So you can make a controllable voltage source. Okay, and that controllable voltage source will work in such a way with the arrows reversed, such a way that it will oppose the fault current. So you can understand again from this diagram here. If you see here, here the half bridge, this if it is made up of half bridge, you can see that the arrows are only in one direction. Half bridges can produce only unidirectional arrows, but full bridge can produce bidirectional arrows. So therefore, in this circuit, even if E has reduced, E has started to reduce, the arrows have become bidirectional, so it can support. So this arrow, this bidirectional arrow is as if the back EMF, and that back EMF is opposing any rate of rise of current through the arm inductors. Okay, this is the other extreme case. You see where E has gone very, very small. So the arrows, the red arrow is bidirectional. It is upside here and downside here. It is bidirectional here. Similarly, the green arrows are upside here and downside here. So both the red and green arrows in a full bridge, it is possible to have bidirectional arrows so that the converter, if E is very small, in spite of that, at least for some time, the converter will be able to control the fault current. But this will not be possible in case of half bridge, because half bridge can only generate one-sided arrows. So that is why I said that full bridge can act like a back EMF in opposing the applied voltage so as to limit the fault current which is not possible with the half bridge topology. That's why full bridge has better performance during fault condition, and that is the reason why people say, in spite of having full bridge as like less efficient, but the fault feature is something which people explore, and they say that do not shut off the IGBTs during fault condition with full bridges. Don't shut off. Instead, use these IGBTs inside the full bridge so that you oppose the applied voltage and reduce the current magnitude. Okay, so yeah, so what you do is you say that okay, you with a full bridge you say that okay, no, you don't shut down the IGBT, but you try to oppose the applied voltage through this, because the full bridge is a fully controllable voltage source. It produces both bidirectional voltage, and you will be able to control the fault current. Okay, so is there any more question? So okay, fine. So therefore, I think you can see this. I mean, if you study the book, apart from the lectures, you should study also some books on MMC or some literature papers. Okay. Unfortunately, since this is a slightly advanced uh, uh, since this is a slightly advanced course, so you may not get all the books easily. Okay, there are not many books on this. In fact, only in 2016 or 17 the first book on MMC came, after which there I have seen a few more books coming on MMC, and I will say that you have to see some of the literatures available in online library, and also try to get some more articles MMC or CHB or something like that. But CHB, cascaded edge bridge, has been there for a long time, almost 30 years that they have been commercially produced. So that is not very new. But MMC is comparatively, even now it is like 13-14 years it is now in existence. Okay. Okay. So in one more question. Okay. What is the difference between common mode voltage and differential mode? Yes, it is common mode voltage is something which is common to all phases. So suppose VA, VB, VC, or let us take two lines, VA and VB. Okay. So suppose VA has a voltage of 1 plus X and VB has a voltage of 2 plus, okay, 1 plus Y, let us say. So then what is the common mode voltage? 1. 1 which is common to all both of them, that is 1, and the differential voltage is x minus y. So 1 plus x minus 1 plus y, that is x minus y. Okay. So differential means difference of two voltages. Common voltage means common to both the phases. Okay. So that is the main difference between common mode and differential mode, which people use very frequently in analog circuits, op-amps, common mode and differential mode. Okay, so common mode rejection ratio (CMRR) is very much used in op-amps, and differential amplifiers are used to collect or to only amplify the difference of two voltages and reject the common mode. Okay, so that is the difference. So here in also this case, if you have a voltage source, so half bridge is producing one DC plus some AC, and another half bridge or another series of half bridges or another half bridge arms, they are producing another DC plus AC. But in the line, you can say that the two DCs are getting cancelled and only the differential mode comes into the, so yeah, in 1 plus x and 1 plus y, you get x minus y. Okay. So what is the, in STATCOM application, if there is no circulating current, then how the capacitor voltages are balanced? In STATCOM with MMC, or I don't know, is he talking about STATCOM with MMC or CHB? See, in STATCOM with CHB, there is no circulating current. So you cannot have a circulating current because CHB by its own structure has no circulating provision for the circulating current. Now in MMC, if it is an ideal statcom, let's say that is an ideal statcom, then there is no active power which is to be given, and so there is no need for any circulating current. You are correct in that there will be no circulating current in an ideal statcom. But in a real statcom, what will happen is that there are losses there are losses in the cells. So when there are losses in the cells, the some active power needs to be drawn from the grid to the MMC, and this active power, and then there will be so you will see how will you distribute this active power between all the 6 arms, and so you will see that you will make a sorting and say that okay, which capacitor has the largest voltage, which capacitor has the lowest voltage, and accordingly you will divert the energy into that capacitor which has less energy, which has less voltage, and so that the sorting algorithm has to be played there. Okay, because you have some incoming energy which you want to distribute evenly to all the arms first, and then you want to distribute it evenly to all the cells. Okay, so that no capacitors diverge from there. So that is what is this STATCOM. So the STATCOM application, there will be also a circulating current once you start to assume that the converters have losses. There will be a circulating current. Please mention the particular application of single phase ML multi-level inverter operating at medium and high power application. I have seen very few single phase multi-level inverters. I have seen very few, okay, to be frank. Usually it is 3-phase, because in 3-phase with 3 wires you can carry 3 times the power, but in single phase with 2 wires you can carry 1 times the power. So it is not I have hardly seen, except for traction applications, there you can use multi-level converters. So single phase multi-level converters operating, I can give you only the application of traction converters, where single phase catenary is there, 25 kV, you take it 25 kV 50 hertz. That is the only, I think that's the only application which I have seen. Otherwise all are generally 3-phase. Okay, next questions. Sir, during operation of say 555 healthy condition, it is mentioned in the slide that converter neutral and load neutral are at same potential. But there is always an instantaneous polarization between converter neutral and load neutral. No, so during operation of say 555, okay, with 555, okay, so what we will say here, there is always an instantaneous potential difference in converter. Okay, you are correct. So when I said that with 555 the converter neutral and the fundamental neutral and the load neutral are at same potential, what I meant to say was that there is no fundamental voltage difference, fundamental frequency voltage difference between N and O. Whatever we had drawn, that triangle, from where we said that okay, V N O, there is a potential difference, whatever we drew there, remember that is a fundamental frequency phasor diagram. That is not an instantaneous quantity, it's a fundamental frequency. So that's why we could have drawn that phasor diagram there. So that NO potential, definitely there is always an instantaneous potential difference between N and O, that is creating those notches and harmonics, whatever. So this one is when I said that in 555 there is no at the same potential at the fundamental frequency. At fundamental frequency, if you draw the phasor diagram, then N and O will coincide with each other. Okay, that's what I meant actually. At fundamental frequency, phasor diagram, they will coincide with each other. But if you go to a 532 or some 544 operation, these in the phasor diagram, they will shift away from each other. That means at the fundamental frequency, there will be VNO of fundamental frequency magnitude. That will come. That's what I tried to mention there. Okay. Instantaneous voltages will always be there. Yes. Okay, I think then yeah. So if you have more questions, you please ask on the forum, and I repeatedly see those forums, and I will ask. I will answer these questions. So thank you for joining, and I think some of the doubts have been clear, and we of course uh, being in a very artificial environment, this classroom teaching is not possible because of these online courses which we enjoy. The classroom teaching is where you go on the question answer, which we enjoy more, much more. But anyway, I hope some of these doubts are clear, and I hope you will learn something more from the course. Okay, thank you.